All right, so the other day we started to look at what makes a power amplifier, and really we started looking at this concept of load line analysis. And we saw what happens if the load line was too shallow. We're able to swing all the way through the voltage, but not all the way through the current. And we noted that that meant that ultimately we were presenting too large a resistance to the power amplifier. It gives us more gain, but lower output power ultimately. And then we said, okay, well, what if we have a slope for the load line that's a little bit different? So we make a steeper slope for the load line. And now you see you can swing through all the current levels, but you can't swing through all the different voltage levels. So they call this voltage limited. We get full current swing and lower voltage gain. So up here, I noted more gain. I want to be specific that we're talking about voltage gain here. That might also lead to more power gain, but ultimately still lower power, lower saturated output power. On the current, on the voltage limited case, we're saying lower voltage gain. We have a lower impedance. That might mean we get more current gain out of the device, but we're and might ultimately lead to higher power gain, depending upon the conditions. But it's always going to lead to lower saturated output power. So we get optimum PSAT, or at least the highest power, highest PSAT we can achieve when RL is exactly equal to R opt. And it's important to note that this is not necessarily, I would say, even likely to be the highest gain point. Okay. All right, so let's look at what the real challenge of a power amplifier design is when we start using silicon, in particular CMOS in our case. But really it's challenging with all silicon. So a typical Wi-Fi power amplifier must deliver 17 dBm of output power. How much is this in watts? So 10 dBm is 10 milliwatts. 20 dBm would be 100 milliwatts minus 3 dBs would be 50 milliwatts. Oops. All right. Now, this is particularly for the 2.4 gigahertz Wi-Fi band. You can actually transmit at higher power in the uni bands at 5 to 7 gigahertz. Wi-Fi exists in both of those bands. So we're talking about the ISM band at 2.4 to 2.48 gigahertz. We can transmit 17 dBm, 50 milliwatts linear power into a 50 ohm load. Now, we know that the signal that we are going to transmit through the power amplifier has a fairly bad peak to average power ratio due to the modulation that we're going to apply to it. It turns out that the peak to average power ratio for the modulation is somewhere around 8 dBs. This is for the old Wi-Fi standard. What existed in 2.4 gigahertz band is typically what we would have called 802.11g back in the day. And the maximum modulation encoding standard for 802.11g was a 64 subcarrier, 64 QAM OFDM base signal. If we need a PAPR of 8 dBs, this implies the PSAT ideally would be equal to 25 dBm. So 25 dBm, it's the linear output power plus the PAPR. Now, in reality, this probably needs to be a little bit higher than 25 dBm because most PAs we can't operate directly up to saturation. We have to add some margin or back off power into the mix. But for the time being, we'll say this PA is perfectly linear up to the point where it saturates. All right, so for a Class A amplifier, or even a Class B amplifier, the output power is equal to the RMS voltage squared divided by the optimum termination resistance. So this is that load that we put directly at the drain of the power amplifier. We're probably going to do that using a 50 ohm load in a matching network ultimately, but this is what we present right to the drain of the transistor. The RMS voltage is equal to V peak divided by square root of 2, and V peak is equal to VDD minus V knee. We are going to assume V knee is negligible. So we're making this really very optimistic right now. Okay, so we can, rearrange some things here and ultimately show that VDD is equal to square root of 2 times P out times R opt. And let's say that we just chose a resistance of, we just presented 50 ohms to the transistor for not necessarily opt. We're just going to throw 50 ohms and see what happens. All right, so this would imply that the supply voltage would need to be 2, I didn't say this, but 25 dBm is about 316 milliwatts. 2 times 316 milliwatts times 50 ohms is approximately 5.6 volts. All right, now, what we're ultimately saying here is that the power is that the voltage supply that we would need if we were just using a 50 ohm termination resistor in order to achieve the desired output power would be 5.6 volts. All right, what's the supply voltage for your process? The maximum VDD?
0.9.
0.9 volts. All right, 0.9 volts for your process. It's even lower for 12 nanometers or smaller FinFETs. And, to make matters worse, of course, the knee is not equal to 0 volts. It's dependent upon the size of the transistor and the current we're running through it. But it's probably somewhere on the order of, 0.2 volts. All right, so our solution is going to be, we're not going to terminate the transistor with 50 ohms. we're going to learn what the R-opt is for our device by, at first maybe just doing something as simple as running some IV curves or simulations for IV curves and figuring out what the optimum termination resistance is, and we're going to match from 50 ohms to the optimum termination resistance. All right. Now, ultimately, what are we doing here? By transforming from a high impedance to a low impedance, we're going to be reducing the voltage swing down to levels that can be supported by a smaller supply voltage. And at the same time, we're going to be increasing the current swing. Now, we haven't really maybe mentioned it before, but an impedance transformation network is doing the same thing that an ideal transformer does. It's stepping down the voltage in one direction and up the current, or it can work in the opposite direction as well. It can step up the current and down the voltage, or whatever the opposite of what I just said was. So our impedance transformation network does the same thing. As we move from a higher impedance to a lower impedance, it's changing the voltage level from a higher level to a lower level. All right, so we can calculate what our R-opt would be if we were using, say, our process that we've been talking about. So we can say R-opt is equal to VDD minus VNE squared over 2 times our desired saturated output power. Now remember, I'm still not adding in any margin for back off linearity, so this is still optimistic, but it'll prove the point. So if we use a supply voltage, I'm just going to say that our supply voltage is 1 volt minus 0.1 volt over 2 times 0.316, our power in watts. This is equal to 1.3 ohms. All right, so we need to do something that's going to transform the impedance of our 50 ohm load down to 1.3 ohms. Remember that we didn't account for extra back off. We also didn't account for losses in the matching network. We are not accounting for current division because we're going to put a 1.3 ohm resistor at the drain of the transistor. The transistor is a current source that has a finite output impedance, which means that there will be a current division that happens where current goes into the finite output impedance of the transistor rather into the load where we want it to go. So those two things are not being accounted for. Now, we know that we're going to transform from 50 ohms to 1.3 ohms. This requires a 6-to-1 impedance transformation. Remember, we're transforming as n squared, so we need something like 6-to-1. All right, so let's see what the real problem is. Now let's add some losses into the network.
All right, Professor, can you explain why is it 6-to-1?
Yeah, 50 ohms divided by 1.3, take the square root of that.
Oh, okay, thank you.
It's close to 6-to-1. I'm sure that I rounded somewhere. Okay, so here is our new power amplifier circuit. We're going to do an impedance transformation, and we have our handy 6-to-1 impedance transformer. We can make this out of an LC network if we want to, but here we're going to use a transformer. And I'll show you in a few moments how to make a transformer in Cadence. All right, so let's assume that we've designed a really nice transformer, but even a really nice transformer in CMOS is likely to have something like 1 ohm of resistance just due to the metallization. So if we just have a piece of copper that's making our transformer, it's probably going to have 1 ohm. It's a pretty small amount of resistance. All right, we want to radiate from this thing 300. I shouldn't say radiate from this because the antenna might have gain. We want to deliver at the antenna, which has a 50 ohm impedance. We want to deliver 316 milliwatts to the antenna. Right. Now we can step the voltage and current down. What we will ultimately end up finding is that we have about 79 milliamps of current flowing through the secondary, and we have about a plus or minus or a 4-volt swing, 4-volt RMS swing. Just in doing the math, and that's just figuring out what the IV relationship is from 360 milliwatts into a 50 ohm resistor. We're doing a 6-to-1 impedance transformation, and so we're going to step the current up on the other side of this. So we're going to have more current over here. In fact, about 474 milliamps, but the voltage swing is going to be about 0.67 volts. All right, so let's figure out what the power is from of our loss. All right, well, 1/2 I squared R is a good estimate. So in the primary side of this thing, we have 1/2 474 milliamps squared times 1 ohm, or about 112 milliwatts of power loss. So this is just lost. This is just power dissipated as heat in the coil. All right, so if we're using a Class A amplifier, maximum efficiency just of the transistor itself is 50%. That's the most it can do. We'll look at a Class A in just a few moments. All right, so let's figure out our DC power consumption for this whole circuit. All right, so we have the output power plus the loss power. These have to, this is what we have to support in order to put 316 milliwatts at the load. and the efficiency of the amplifier is only 50%. So this is 316 milliwatts plus 112 milliwatts divided by 0.5, or about 856 milliwatts. All right, so we have to generate, or we have to use 856 milliwatts of DC power in order to generate 316 milliwatts of AC power at the antenna. That's what we're finding here. So we can find a new efficiency of the antenna, and this is now including the matching losses. This is how we would start to calculate that. I'm just going to call this the new efficiency. This is 316 milliwatts. That's what we're actually delivering to the antenna. And we have 856 milliwatts, or the efficiency is 36.9%, just from including the matching network losses. Not great. What do your CPES folks think that they need for a DC to DC converter?
99.
They complain if it's not 99.99%, right? Yeah. RF amplifiers are definitely less efficient. All right. This is the saturated efficiency of the amplifier. As we start to back the power down and use modulation waveforms that have peak to average power ratios, we're going to operate it at an average power that's much less than its peak power, and it's going to get less efficient. So as we start to decrease the power in an amplifier, they call it back off. You're backing off from saturated power. So you'll see that term sometimes, back off power. All right, the key takeaway here is just, and we still haven't, by the way, included current division yet. This is just matching network losses. All right, so we need twice as much DC power as the power we're delivering to the load ultimately in our very optimistic looking power amplifier right here. And that is ultimately the challenge of designing power amplifiers in silicon. We have low supply voltages. We have to use impedance transformation in order to get power out. The transformation itself is lossy and becomes lossier as the quality factor of the network increases. And so we're going to look at ways to increase the efficiency from a topological perspective, or other things that we can do to try and increase the efficiency. How many of you have heard of 3.5 power amplifiers? Anybody know what a 3.5 device is? Gallium nitride. Have you heard of gallium nitride? Gallium arsenide, indium phosphide. Those semiconductors all have what's called a large band gap or a high band gap, at least higher than silicon. That means that they can operate safely from higher voltage levels, even with similar feature sizes. So that's why those devices are typically chosen for RF power amplifiers rather than CMOS. They can work with higher voltages, and it's just a huge advantage. All right, well, we are making things in CMOS. CMOS does have advantages because it's scaled at a much more aggressive rate than gallium nitride or gallium arsenide have. It's smaller, and so it has shorter channel lengths, typically means it's faster. So we can't necessarily make higher power, but we can make higher speed or higher frequency amplifiers.
Is it cheaper?
CMOS is way cheaper generally than 3.5 devices. The 3.5 devices, CMOS, modern CMOS devices are typically made on 450 millimeter wafers. Pretty big. And the area of a wafer is pi r squared. The standard wafer for 3.5 devices is more like 150 millimeter or something like that. It's much smaller. So you get far fewer devices. The material, the wafers themselves cost more. So yeah, CMOS is way cheaper. Yield is higher for CMOS also. All right, so let's look at a Class A amplifier. So here, as I show you these amplifiers, you're going to look at them hopefully and say, oh, these things all look pretty similar. We just have a matching network going to the drain of a transistor. We might ultimately cascode this. We probably will actually cascode it if we're going to make a power amplifier stack devices. But for now, we'll just start with this. Now, normally for a big power device, you're going to have some parasitic cap here, CP. As we showed the other day, we probably try and take the shunt inductor L1 and resonate it with that capacitor. And then this network, ultimately what we're trying to do is transform this so that as we look into this network, we see R opt. So we're canceling the reactance of the device using the shunt resonance with L1, and then we're using a tapped capacitor match to make an impedance transformation from 50 ohms to R opt. You can use any topology that you want. Most power amplifiers will use a DC block of some sort, so C2 is very necessary there. If we didn't have C2, what would happen? We'd have the DC voltage shorted directly to a 50 ohm resistor, and we'd be wasting a lot of current just to feed a 50 ohm resistor. Yeah. At the input, you can see also I probably have a 50 ohm source driving this, at least for right now. In the end, I'd probably have a driver amplifier that would be doing this a bit more efficiently. But in order to match to that amplifier, I've added a 50 ohm resistor shunted to ground at the input. Remember, we said this was bad for an LNA because it capped the noise floor. It made the minimum noise floor 3 dBs in doing this. But for a power amplifier, we typically don't care too much about the noise floor. We do care about it because ultimately whatever noise comes out of the power amplifier goes into the antenna and gets radiated. So we don't like that. We do need to minimize it. But for the time being, good match. It works. Now, for a Class A amplifier, the definition of a Class A amplifier is an amplifier whose current never cuts off due to any input voltage. All right, so we're going to bias the gate to source voltage through this 50 ohm resistor at some level that allows the transistor to never cut off. All right, so if we look at this, ideally what would be happening is the drain voltage would be swinging through its full range. And the drain current should be out of phase with the drain voltage. Swinging through its full range. It's got an average value of IDC. Oh, I'm sorry, this is not right. It's out of phase with the input voltage, but not necessarily out of phase with the output voltage. Anyhow, it doesn't matter. We'll leave it that way. All right. Why does the drain voltage swing up to VDD, up to 2 VDD as I've drawn it? Yeah,
Because of the resonance.
it's not because of the resonance, although the inductor is playing a role in this. The DC value at the drain of the transistor has to be equal to VDD because the inductor is a short at DC. And since it can swing all the way, since the conjecture is it can swing all the way down to a low voltage, it has to be able to swing all the way up to a high voltage to maintain the same DC level. Yeah. All right, so biasing through an inductor gives us free voltage swing. That's good. Now, we might need to take care of that. Our device might not be able to handle that voltage swing, so we might need to be careful. But we get free voltage swing using the inductor. All right, so just as before, our output power is always the RMS voltage squared over the optimum termination resistance, assuming that we have a sine wave or a sine-like wave, driving into a resistor. This is V out peak squared over 2 times R opt. So I've just converted from RMS voltage to peak voltage with a factor of a square root of 2. And we know that V out peak is equal to VDD. Now here I'm kind of neglecting the fact that there is a knee voltage that isn't quite 0 volts, but we're just doing hand analysis, so it's okay. All right, we plug everything in, we can find R opt is equal to VDD squared over 2 times P out. We can also find that PDC, the DC power, is equal to whatever our IDC is times VDD. Just the definition of our DC power consumption. And we can further say that that DC current level is probably equal to VDD over R opt. All right, so if we define drain efficiency as output power divided by DC power, then this is equal to 1/2 times V out over VDD squared. Now V out max is equal to VDD, we already said, so eta of a class A amplifier max is equal to 50%, and it rolls off as the square of the output voltage. So as we reduce the output voltage from peak, the efficiency is reducing as a square of that voltage. All right, to design a class A amplifier, it's pretty straightforward. We're given an output power and a supply voltage. We just choose the optimum termination resistance, and we size the transistor so that it can deliver the current that it needs to be able to deliver. And then we're going to set VGS so that we get that maximum voltage swing. All right, so an example class A amplifier. We're going to assume for the time being that the mobility of a device, of the devices that we're looking at, is around 1200 microamps per volt squared. Is the mobility of these devices 1200 microamps per volt squared? It really depends upon how you're biasing them. The square law of a MOSFET that we all learned some time ago does not apply to modern devices. So we'll just assume this for the time being. It's a reasonably good assumption to get us started. But in reality, you'll have to do some simulations. Yeah.
Like talking about being out the out or square.
Mhm.
He said the out can go up to movie.
V out, sorry, the RMS value of V out. Yeah. Yes. Not the peak value. Yep. You're right. You're right to question, but. Okay, so we want our output power again to be 316 milliwatts. So let's say we're designing the same exact power amplifier that we were before. We can plug our numbers in again. VDD minus VNE squared over 2 times P out is equal to 0.8 squared over 0.732 is 1 ohm. I like numbers to work out very nicely. It's close enough. We're ultimately going to do hand calculations just to get us a nice starting point, and we're going to move to the simulator as quickly as we possibly can. So it's important to do the hand calculations to know that you're in the right ballpark, but beyond that, the simulator will refine the design. So we said before, IDC is roughly VDD divided by R opt. This is 1 volt divided by 1 ohm. I'm getting very precise here. A lot of zeros. Can't do that. All right. 1 volt divided by 1 ohm, approximately. So we need 1 amp of current. All right, now this is our DC current level. Let's just assume that the current can swing all the way down to 0. Stands to reason that it can also swing up to twice IDC. So I peak is equal to 2 times IDC. The MOS device needs to provide that. Any transistor we were using needs to provide that, but in our case, the MOS device needs to provide that. All right, now I know I just told you square law is meaningless for these devices, but it's the best equation we have on hand for the time being. So ID is equal to 1/2 mu n Cox times W over L times VGS minus VTH squared. We'll leave off channel length modulation. So we can find W over L by inverting this whole equation. You need a transistor width over length that's approximately 83.4 thousand.
Or more.
Is that a problem? The total periphery of this in our process, so you have to remember that the L is 20 nanometers. So, even though this is quite a big ratio, we can make this device on chip and it won't actually take up that much area. The inductors that we use in the matching network will still be bigger than this thing. So that's okay. Bad, we do need a very big device, but we can live with that. It's something like 1.6 millimeters width, 20 times 20 nanometers. The area ends up not being that bad. All right, now, what is the bad news? This is optimistic, right? We still didn't take into account current division. In this case, we didn't even have the losses in the matching network. And any other second order effect we're not thinking of. All right, so how do we take those into account? I don't typically do any hand calculations for these things. I write MATLAB scripts. So I can calculate all these things in MATLAB and I can write loops that will loop through and say, if I need this much output power, I'm going to need this impedance presented to the transistor. That's going to result in a matching network loss of X, Y, or Z. And I just iterate through the loop until it finds a device periphery that does include the effects of current division, matching network losses, etc. All right. And more to the point, I typically will write these things using GM over ID based lookup tables. So I'll look them up. I'll look up actual device performance and not assume 1200 microamps per volt squared for mobility. We'll get a more accurate lookup table based design. All right, I want to pause there. We might come back to power amplifiers in just a moment, but I did want to open up Cadence and show you a couple of things. So I did finally get a video posted on designing for optimal noise figure. And I posted, there's a Cadence-based tutorial on doing LNA simulations as well. So you can follow through that. But I'll open up a design and show you. How have the servers been working for folks thus far this semester? We haven't been taxing them too heavily yet, but okay.
So far is good.
Yeah, I had a couple times where they were down, but it seems lately they've been better.
Yeah, they've been doing a few things to optimize them, so hopefully they'll stay that way through the rest of the semester. If not, we'll find some solution. I do have the ability to run on ARC. I just don't have the ability to control to use chown or chmod, so I can't control proprietary information very easily. And I don't want to go to jail.
Did it all become Dr. House students?
Good. There are worse things. There are worse things. Dr. Ha's a good advisor. Okay, so oops, maybe in the wrong library. Mastering network. Okay. This is my library manager. So I have this, no, that's not the right one. What's going on? I guess it is right. Oh, okay. I know what I did. I added another library here. All right. So by default, this RF examples library is loaded into Cadence. The tutorial more or less follows this thing. I wanted to talk a bit about some practical things first. So we're making a U-turn. We're going to talk about LNAs for just a few moments. Here is a simple LNA topology. I am basically making a current mirror to bias the LNA. So the LNA devices are these ones on the right side, and these devices are just a reference voltage generator to generate the bias voltage for the LNA. We run a current of 1 milliamp into the diode connected device right here, and it creates a VGS that is proportional to create a current that ideally would be equal on the right side of the circuit. This is a simple way to match or to do a DC bias of an LNA. Now, you can do things like scale the devices. So if you don't want to use very much current in this path, you can, make the current here 10 times less than you want. Then you make these devices 10 times smaller, and then the current will scale accordingly. I have my input port going into my LNA right here. I put a big resistor towards the direction of the current mirror in order to keep the signal from wanting to go in this direction, and said it will go towards the lower impedance path in this direction. And for right now, if I'm just trying to do some parametric studies of the device, I put a choke at the drain of the transistor, and then an AC short, going towards the load. What is a choke and what is a DC short? You want the choke impedance to be about 100 ohms or more, or something like that. The DC short should be like an ohm or something like that. That keeps the AC signal wanting to go this direction and not this direction. You can make it bigger if you want. Won't hurt too much. All right, so it turns out for low noise amplifiers, there is an optimum current density in order to achieve a minimum noise figure. So in the video, I kind of show you how to achieve that current density, or how to find that current density. Namely, I'm going to turn off the corner simulation here. We just set up an S parameter simulation as you've done before. Theoretically, as you've done before. I can open it. There we go. So most of this stuff is the same as you did for homework 1 and homework 2. The difference now is we're going to specify a slightly different frequency range. I'm going to design an LNA for the uniband, 5 to 7 gigahertz. And we're going to enable do noise on this. So it will do a noise simulation. You have to tell it what the ports are. These should correspond to whatever the labels for your ports are on the schematic. And in our case, also, we're doing a single-ended design. You have the opportunity to do mixed mode. We'll look at a transform in just a moment. All right. So with this, it will now run a noise figure simulation. I don't know that I've asked this. What is the noise figure of a passive component? No, let's say a lossy passive component. Yeah, you're on the right path. So it's loss. The noise figure is its loss. So for instance, if you have an attenuator that has a noise figure that has a loss of 2 dBs, its noise figure is also 2 dBs. That's any passive component. If you have a filter whose insertion loss is 3 dBs, the noise figure is 3 dBs. Okay, so this is our amplifier. Now, I'm plotting, I have it set to plot these already, but if we go to results, direct plot, main form, we have on the S parameter form here a lot of different things that we can plot. So obviously some of these are related to the reflection coefficient and whatnot. But in particular, we're going to pay attention to NF min. This is the minimum possible noise figure that this circuit can provide. Now it's the whole circuit, but ideally our signal is going, into the amplifier and then towards the output because we've put such a big resistor here. So the noise figure min is just what is the minimum that this thing could possibly ever provide. Not what it's providing right now. Let's plot what it's providing right now. To make a sub window here. All right, you can see quite a stark difference here. The minimum that the amplifier could achieve is something like 0.4 dBs, and with the impedances that are presented to it right now, it's about 6.2 dBs. You know that your design is good when your actual noise figure is getting close to the minimum achievable noise figure. G max is the maximum gain that you can get from the input port to the output port. This is taking into account mismatch losses. So it's a nice way to look like, what can this device give me? Possibly. It's the best case. You can, of course, see what it's giving you right now. We can just go and look at S21. Oops, I put it in the wrong plot. Oh. All right, so you can see we're not matched very well. That's what's causing most of this reflection. And because of that, it's actually got some loss and poor noise performance. But the nice thing about that method is you have a way to quickly look and see, like, what can it do? Well, there's the device itself has a noise model internal to it. And then there will also be some attenuation from the network that's happening. So it's taking into account all of those things. It's more or less doing the same calculation that you're doing on your homework this week for the various amplifiers in part 1 of the problem. It's finding how much output signal am I getting with all noise sources included relative to how much I'm getting when I only include the source resistance. Okay, now some other things that will help you as you start doing design are these corner simulations. So to enable corners, you can click on the checkbox and you can set up a corner. We'll open up this particular corner here. Theoretically, okay, there we go. So in this case, I'm ultimately trying, in this example, I'm trying to show you how to find the current density. So we're going to sweep the width of the device and the current going through the device, and we'll find the combination of current and width that give us the lowest noise performance. If we want to add some different corners, there's a little thermometer here that you can click, and you can add another sweep to this. We'd have to add another variable. We don't have one. If we wanted to add another variable, we could go back into the schematic and add that. But you could sweep. You can always sweep temperature. So we could, sweep temperature. If you put a space between the numbers, it will just do each of the individual numbers. You can also set them up as arrays to sweep through, like I've done with the other example. So in this particular case, it it would calculate noise figure at minus 40C, 25C, and 100C. Let's see what that looks like. I'm not sure. Corners might take a little bit longer. I do also show you how to do this, but in the setup, if you want, you can go to job setup, change the job control mode to ICRP. This is just how it distributes the job. And for some reason, there's not any real good reason why this works better on our servers, but it does. And you can change the maximum number of jobs to some number bigger than one. And all that does is it means it will run multiple simulations in parallel. All right, we can look at our, you can see, of course, well, the gain gets better at low temperature. That makes sense. What do we think the noise is noise better at low temperature or high temperature? Low temperature, there's KT somewhere in there, right? So minus 40, quite a substantial difference, right? 0.27 versus 0.38. Yeah, pretty good. All right. Okay. All right. Any questions on these things? I'll do a video shortly on doing an IIP3 or a nonlinear simulation as well. And you can start doing that tutorial if you want more coverage.
Professor, what's the main difference between noise figure and noise figure minimum?
So noise figure is the actual noise figure that the simulation is giving you right now. Noise figure minimum is the minimum that it could possibly ever be. If you terminated the transistor exactly correctly, that's what it would be.
If noise figure is closer to noise figure minimum, that's a better design, right?
Yes, that means that you've achieved a more optimal design. So the closer that you can make NF to NF min, that means that you're achieving, optimality.
All right. So what is the maximum difference we can say that, well, it's a better design?
Well, I don't think I'd make any kind of qualification on that because ultimately, in order to achieve a certain minimum, you might need to burn more power, right? So it's really, if you have a spec, you need to try and achieve that spec without costing too much in other regimes. So, for instance, you might not need to to operate at the optimum current density with a high amount of current. You might be able to lower the amount of current and still achieve a good enough noise figure, for whatever your spec is. So an optimum design is not an over design. It's one where you taking into account all possible aspects of the design. In the military or defense community, they call this size, weight, power, and cost. So.
All right. Thank you, Professor.
Of course. All right. So let's look at how to make a transformer. I'm going to make one just a balun. All right, so from analog lib, we're going to add some inductors. Now, we want big inductors for a transformer because we don't want signal leaking into the coils, so we want the impedance to be high. I'm going to make these 400 microhenries. That makes the impedance, I don't remember what the number is, but quite high at about 2 gigahertz. So I'm going to put 2 inductors down here, 2 inductors down here. And these inductors have dots on them. And the dot convention is just that the current flows into the dot. So if I couple these 2 inductors together, current flowing into L0 will flow into the dot of L2. And there's a component in your libraries called MIND, that's mutual inductance. And the way that this works is you give it the name of two inductors and a coupling coefficient. We're going to make this an ideal transformer. So I'm going to have L0, L2, and I'm going to give it a coupling coefficient of 1. That means that these two inductors have exactly the same inductance, so they have the same turns ratio, and they have a coupling factor that means that the signal will ideally couple from one side to the other. I'm going to add that mutual inductance there, and I also need one for L1 to L3. Now, there's a reason I'm doing this with 4 inductors instead of 2. I'm not making just a transformer. I'm going to make a balun that's much like the ideal balun that you have in the analog lib kit. So we're going to wire this. I'm going to add 4 ports here, P1, P2, P3, and a center tap. Actually, let's do this as P plus and P minus. So P1, let's make this even more specific. Pn, P plus, P minus. And CT, center tap. Our input. All right, and then I'm going to add a label. I'm just going to tie the other side of this input to ground. I could add a port there, but I want this expressly to be single-ended in, differential out. Right, there is our transformer. Done. Yeah.
Why do we need 2?
Why do we need 2? I could, but then I don't have a place for a center tap. Okay. Yeah, so I'm making a balun now that I want to be able to pass DC through at some point. So what this allows me to do is if I had a DC bias that I wanted to pass to something, I could put the DC level right here, pass that in, that will go to whatever, that DC will be shorted right through these inductors, go to its target, but the AC signal will expressly be differential. So I'll have if I put a plus going signal in here, it'll be plus at P plus and minus at P minus. So in phase at P plus, out of phase at P minus. All right, now if you want to be able to use this over and over again, you can go to create, cell view, from cell view, and then if you want, you can make it look pretty. You can, add some decoration to it, or you can just leave it as is. It'll work the same no matter what. All right. Now that one is in my library. You can use that if you want to, or you can make your own to give it a try. You would instantiate it just by opening up or adding an instance, pointing to the correct library. I call this XFMR balun, and then you could drop it in. Okay. Now, I do want to point out that it's not entirely necessary to do something like this. Cadence does have one of these in. But there's this under analog lib, and it's called ideal _ balun. And I don't like it because it looks a little bit funky. But for the ideal balun, the 2 ports on the right, those are your P plus and P minus. Your input is in the top left corner. And if you want, you can put a DC voltage in at the bottom left corner, and that will feed the center tap. I just think it's a little bit clunky and it doesn't look exactly like what it does, so we can make our own. The other thing about this is that this is an ideal bail-in, meaning that it's not a narrow band bail-in, which the bail-ins that you're going to be using on your designs are all going to be narrow band bail-ins, meaning that they're going to be made from spiral transformers. So you're not going to be able to achieve 400 microhenries of winding inductance. So if you want to make your simulations more realistic initially, you can make your own bail-in and assign whatever value you want to the winding inductance, and then you could resonate it with a cap, for instance. One other thing that's useful. I'm just going to copy this bail-in. I call this xformer bail-in underscore par. No, I didn't want to copy the symbol view. Delete it. All right, I'm going to, now, what do you do if you do want to, say, change the winding inductance or something like that, but you want to be able to tune it? If you go in and make the inductance, you can use you can make this P par and then some name. You get lazy, you can select 2 of them at a time, hit the properties queue, change apply to all selected, and you can change the properties for both devices at once. EPAR LSEC. And I could even make all right, so now if I go to save and create cell view from cell view, all right, so it'll make a new cell. If I go and put that into some other design, now we have parameters that we can use. So I can, and this is nice because now, let's say I wanted to make this a 2-to-1 transformer, okay? 200 micron, 400 micron, K factor of 1. I can start playing around like that. Okay. All right, so as we start to head into the second half of the semester, we're going to start using a lot more active devices. So there will just be a stream of videos that will start to come up on how to do these little things in Cadence. And they'll correspond more or less to when you have a homework due. So we have LNAs. We're going to have some for PAs coming up soon. I'll put up the Cadence tutorial for PAs and start working through those things. All right. Well, we are just about out of time. So we will pick up starting on Class B power amplifiers right after spring break. We'll start then looking at Class C, and then we'll look at switching amplifiers. Then we'll hit mixers and VCOs, and that will cover almost everything that's on an RFIC, and hopefully you'll start, working through your projects and being able to tinker with your designs to see what's really on it. Reverse engineer an IC. That's the goal. All right. Have a good spring break. If I don't see you, I will be available online for the most part. I will not be in the town of Blacksburg. I will be in Solitude, Utah. See you after the break.
Thank you, Professor. See you.
Thanks. Have a good one.
Yeah, you too.
I have a couple of stupid questions.
Oh, what happened to my video? Weird.
Yeah, that happened right after you opened Cadence, so I found it fitting.
I hope it's not that fitting.
No, I was thinking if Cadence is working.